Okay, part 2 of chapter 7. Let's talk about energy. The universe is made of matter and energy, and in fact, matter and energy are two different representation of the same physical concept. Matter and energy can transfer to one another, can transform to one another. Matter is the stuff we can see, smell, taste, and feel. It has mass and occupies a space. It is condensed, and but energy, and it can transfer to energy. So energy moves the matter. Okay, energy can be transformed or transferred, but never created nor destroyed. So the amount of energy that was first produced or created in the first moment at the Big Bang has not been changed since. It has changed its form. Some of them has changed to energy. Some of them has changed to matter, because we have sun, planets, and things that we can see around us. It used to be energy at the beginning. So energy comes from many things: sunlight, food, heat, sound, electricity, radiation, and many other things. We have different types of energy. We have kinetic energy. Here in this chapter, we're only talking about two types now. Kinetic energy, which is associated with a moving object, and a kinetic energy we just showed with K, or KE, kinetic energy, or just K, that is half mv squared, half times the mass times the velocity squared. Okay, and then we have potential energy associated with the position of the object. Okay, there is a change in energy when the object changes its position. And normally we deal with gravitational potential energy. So gravitational potential energy, they use P, other books use U. I am going to use U to show it. It is mgh, mass times g, gravitational constant, 9.81, and h is the height of the object. So this is the formula for potential energy, right? And this is for kinetic energy. All right. Work done by gravity is usually negative. Okay. So in other words, let's say that I have a box with mass m, and it is moving from height 1, or hi, to this point upward, or h of final, or h2. And I know that mg is down. I know that. Okay, so if I want to find the work done by mg, I have to write fd, or fd cosine theta. Okay, f is mg in our case, d is displacement upward, and they have the angle of 180, so I have cosine of 180 here. So I have mg, the displacement is final height minus initial height. So I have h final minus h initial. Cosine of 180 is -1. So I have negative mg h final minus h initial. Okay, so depend on the displacement, either up or down, you can have a negative or positive value for work done by gravity. Okay, sign of the energy. Is it possible for a kinetic energy of an object to be negative? Is this possible for a kinetic energy to be negative? So let's take a look at what the kinetic energy's formula is. So K is half mv squared. Okay, half is always positive, right? It's a number. M, it's the mass of the object, which is always a universal number, which is always positive. And v squared, even if the v is negative, since it's going to be squared here, it will be positive. So positive, positive, positive. It cannot be negative, okay? So the answer is no. By what factor does the kinetic energy of a car change when it speeds triple? So let's take a look. This is the kinetic energy initially. So I have mv squared. Now finally, the final position, I have half m. V is tripled, so I have 3v now, not just v, 3v squared. So I have half m. 3 to the power of 2 is 9, v squared. Okay, so I have 9 times half mv squared. Now I know what this one is. It's right here. Okay, in other words, k of final is 9 times k of initial, because you have 3 to the power of 2, which is 9, so by a factor of 9. Okay. Free fall. 2 stones, one twice the mass of the other, are dropped from a cliff. Just before hitting the ground, what is kinetic energy of the heaviest stone compared to the light stone? In other words, I have 2 masses. One is 2m, it's double, okay? The other one is just m. And they are in a free fall from this point, so they will all fall, all right? And we know they will gain a speed. Initially, they have no speed, but they are gaining a speed with an acceleration of g, which is 9.81 meters per second square. So they will hit the ground with the same speed, okay, and at the same time. But do they have the same kinetic energy? Let's take a look. So the kinetic energy of the first one is half mv squared. So kinetic energy of m. All right. The kinetic energy of 2m, or the one that's twice, is half 2m v squared, because the mass is now 2m. It's not m, it's 2m. So in other words, the kinetic energy of the mass 2m is double of the kinetic energy of mass m. Okay? So twice as much. Not because the velocities are the same. Okay? Velocity is the same, but since the masses are different, the kinetic energies are different. Work energy theorem. So consider a constant net external force acting on an object. Okay, we have a net force or total force or sigma F here acting on an object. The object is displaced a distance d in the same direction as the net force. So I have a sigma F here, or net force here. In other words, I can just write it like this, F of net. Okay, and then I have the displacement of d happening right there. The work is simply having this type of formula here. So in other words, work is F d, okay, and since they are in the same direction, F d cosine theta, this cosine theta is cosine of 0, which is 1. So I have F d, but I know that this F is F of net. So I know that this is net. This is net force. Or I can just write F net as sigma F, okay? Sum of all the forces, or net, okay? And I know from Newton's second law that sigma F, or F of net, is ma, okay? So that's why you see that instead of having sigma F here, I can just easily write ma. All right, so keep that in mind. Let's go to the next slide. So what I found was this. W is sigma F times ma, okay, sorry, times d. And then instead of sigma F, I wrote ma d, okay, the displacement. Instead of having this, I wrote ma. But I can now look at this a times d, acceleration times displacement, and I can remember the time-independent formula, okay? The time-independent formula, which is right here. V squared is V0 squared 2a delta x, or 2ax. So A times displacement, or D, I can show it like something like this. I can write it V squared final minus V initial squared over 2. If you remember the time independent formula, A times delta x, or A times displacement, is V squared minus V0 squared over 2 A times D. So anywhere I see A times D or A times displacement, I can just write it like this, which I have done it here. So I see A times D here, and I wrote it like this: V final squared minus V initial squared over 2 is M. So if you multiply this, 1 over 2 times M to this parentheses, you'll have half mv final squared minus half mv initial squared. In other words, this is the final kinetic energy, okay? This is the final kinetic energy, or K of final, and this is initial kinetic energy, K of initial. So the work done by a force is equal to final kinetic energy minus initial kinetic energy. Okay? The kinetic energy, or KE, or just K, of an object with mass m and a speed v is given here. Half mv is squared final, half mv is squared initial, is equal to it. So in other words, what we have, which I'm going to put stars here, sum of all work done by all the forces, or the work done by the net force, is equals to the change in kinetic energy. Sigma W is delta K, or sigma W is K final minus K initial. Okay, that's what we have here. Okay, so work energy theorem. The work energy theorem: when a net external force does work on an object, the kinetic energy of the object change according to this. So the work done by the net force of on an object is equal to the final kinetic energy minus initial kinetic energy, or the change in kinetic energy. So let's say that I have a force acting on this F-14 Tomcat, okay? Initially it had a velocity of V0, okay? This net force is causing, after displacement of S or D or whatever, causing this F-14 to have V final, or final velocity, okay? So the change in kinetic energy from final to initial, finally it was half mv final, initially half mv initial squared. If you find the change, or delta K, the change in kinetic energy, delta K is the work done by net force. Work, let me actually write it, because delta K is work done by net force, which we have it right there. So let's take a look at this example. The mass of the space probe is 474 kilograms, okay? So that's the mass M, 474 kilograms. And its initial velocity of 275 meters per second, so V0 is 275 meters per second. If a 56 Newton force acts on the probe through a displacement of that much, so force is 56 Newton, okay, or millinewton, isn't it? But I'm just going to use Newton, doesn't matter, it's just a number. Force acts on the probe through a displacement of 2.42, so the displacement is 2.42 times 10 to the power of 9 meters, so it's a huge displacement. what is the initial speed? We have, what is the final speed? We have the initial speed, we're looking for final speed. So I assume that this force is along the direction of motion. So sigma W is delta K, okay? So sigma W is the W of total W done by all the forces, or the work done by the net force. So the work done by net force is delta K is K final minus K initial, K2 minus K1. So work done by the net force is just the force times displacement equals K2 minus K1, or K final minus K initial, doesn't matter. Okay, so F is 56. Displacement is 2.42 times 10 to the power of 9 meters. K final, or K2, is half m v2 squared minus K1 is half m v1 squared. Okay, so I have 56 times 2.42 times 10 to the power of 9 equals half. I'm going to factor out half m here, so half of 474. Then I have v squared, v final squared minus v initial squared. Okay, so I can find this quantity of v2 minus v1 squared to be 2 times 56 times 2.42 times 10 to the power of 9 divided by 474. Okay, then I can move this to the other side. Then I would have v squared final equals 2 times 56 times 2.42 times 10 to the power of 9 over 474. I have moved this with a negative sign to the other side, so I have a positive v initial squared, and we have the v initial here, 275 meters per second, 275 meters per second squared. And in order to find v final, not a squared, I have to put this under the square root. So v2 is just v2 squared under the square root. We know what it is. Okay, so super easy, pretty easy actually. Okay, so a child on a skateboard is moving at a speed of 2 meters per second after a force acts on the child. Okay, our speed is 3 meters. So before the force, initial velocity is 2 meters per second. After force act on her, the final velocity, or v, is 3 meters per second. What can you say about the work done by external force on the child? So the work done by external force on the child, the work done is equal to the change in kinetic energy. Okay, so change in the kinetic energy is positive because you had half m final velocity squared minus half m initial velocity squared. So in other words, you have half m, v squared is 3 to the power of 2, which is 9, minus half m, initial velocity is 2 to the power of 2 is 4. So what you have here is, if you have this, you have 9 over 2m minus 4 over 2m, which will give you 5 over 2m, or 2.5 m. M is the mass of the child, right? We don't know it, but it's always positive. So what we know is the total work done on the child with the skateboard is positive number, okay? So, that's why it's gaining a speed actually, because it's positive. So positive work done on the child. Okay, slowing down. If a car traveling 60 kilometers per hour can brake to a stop within 20 meters. So it's going with 60 kilometers per hour and it's stopping after 20 meters, ending up being 0. It stopped, okay? What is its stopping distance if it is traveling 120 kilometers per hour? So if the speed is double, how much distance do I need to stop? Okay, and we assume that we are using the same force to brake, and the braking is the same force acting in both cases. Okay, so let's see. If I want to write that down, I have sigma f for the first case equals delta k. Sigma f is forces for the net force acting on the work done by the net force acting on the car. Okay, so the net force is just this F that you can see because N upward, so this N up and this mg down are perpendicular to the direction of the displacement. So they have a cosine of 90 and the cosine of 90 is 0. So the total work is just work done by F, which is delta K, okay? Now, that's the first case that we're looking at, by the way. So work done by this force is this force times the displacement times the cosine of theta, which is cosine of 180. Okay, the displacement is to the right, the force is to the left. And delta K is K2 minus K1. Okay, so the force, which is F, the displacement is D, cosine of 180 is -1. K final, K2, it's gonna stop eventually, so the K final is 0. Minus K initial, which is half mv squared or v1 squared, okay? So I have negative FD here on the left, I have negative half m v1 squared, all right? So this negative and this negative will cancel. What I have left is D being half mv1 squared over F. Okay, that's what we have. That's the D. All right. So we'll do the same thing for the second case. We'll do the same thing for the second case. So F D cosine of 180. I don't want to put the dot here, but it doesn't really matter. You know what I'm talking about. F D cosine of 180 is K2 minus K1. Okay. And F is constant. This D is different though. This D is different from the original D. So if I want to specify that, I can just say D1. Okay. And specify here is D2. All right, so F D2 180 is -1. It will stop, so this is 0. Negative half m v1 squared. So F, and this negative and the other negative will also cancel out. So what I have is F D2 is equal to half m v1 squared, and D2 then is half m v1 squared over F. Now, they look the same, but the values for initial velocity in each case is different, okay? So if I want to continue, what I would say is this. I have d1 being half m over f, v1 squared, or 60 squared. Here, d2 is half m over f times v1 squared, but this v1, this second case, is 120 squared. So in other words, since I have multiplied the initial velocity by 2, but this 2 is inside this parentheses, so it will be to the power of 2, and it will come out as 4. Okay, so in other words, I can write this like that. d2 is half m over f. 120 is 2 times 60 to the power of 2. And d2 is half m over f, 2 to the power of 2, and this is 2, by the way, not 1. Making sure this is 2, not 3. Okay, so 2 to the power of 2 is 4. So I have 4 here. So 4, 60 to the power of 2. And if you're looking at this, this is d1, isn't it? So this is d1. In other words, d2 is 4 times d1. So it needs 4 more displacement. 4 is multiplied, whatever it is. It was 20 meters before. Now it is 4 times 20 meters, which is 80 meters. So if you double the speed, you need 4 as much displacement to stop. Okay, the work W0 accelerates a car from 0 to 50 kilometers per hour. How much work is needed to accelerate the car from 50 kilometers per hour to 150 kilometers per hour? Okay, so I want to compare the second one. So let me actually go ahead and change the style thickness of the, all right, so it should be okay. Now, so the work W0, accelerate a car from 0 to 50 kilometers per hour, does that. How much work is needed to accelerate the car from 50? How much work do I need to accelerate the car from 50 to 150 kilometers per hour? How much work do I need to do? So in other words, the W0 is delta K, okay, or K2 minus K1, okay. So W0 is half M, V final is 50 squared minus V initial is 0, so I'm not going to write it because it's just 0, so it's just 0. So work is half M 50 squared. All right. Now for the second one, I have the same formula. Okay, so I have K2 minus K1. So the total work is K2 is half M 150 squared minus half M 50 squared. So I have half M. I can write 150 to be 3 times 50 squared minus half M 50 squared. Okay. Now in this case, This 3 to the power of 2 will come out as 9. So you would have 9 half m 50 squared. One more time. 3 inside this parentheses is to the power of 2, which is 9. And you can bring it out because it's just multiplied with all of them. So you can just write it like that. Minus half m 50 squared. You know already what half m 50 squared is. It's right here. Half m 50 squared is W0. So this is 9W0 minus W0 minus 8 Qs. So, or 8 W's, W0. So, not 8. This is actually incorrect. So the final answer is 8, but it is 9W0 minus W0 being 8W0. This is W. So this is the final answer. All right, so 8W0 for that. Let's take a look at this exercise. Exercise 5, stopping distance. A car is traveling at 7 meters per second. So it's a constant speed of 7 meters per second at that point. So V is 7 meters per second, or initial velocity maybe. When the driver applies the brake, the car moves 1.5 meter before it comes to the complete stop. So the displacement here in our case is 1.5 meters, okay? And final velocity in our case, or V2, is also 0 meters per second because it's stopped. If the car had been moving 14 meters per second, so if the speed is double, the initial speed is double, okay? So that's the initial. If it was like that, if it was 14 meters per second, how far would it have continued to move after the brakes were applied? Okay, so it's literally the same thing. So we wanted to know how far would it go to get to the final speed of 0 again. So the initial velocity is double, just like what we had. Now, the D2 should be 4 times D1. So we just proved it in the previous problems. So I think it was right here. So 4 times D1, it's the same formula, it's the same physics, different numbers. So D2 is D1 times 4. So 4 times D1 is 1.5 meters, okay, which is 6 meters total. Okay. So work done on an object is this, FD cosine theta, which is a constant force applying on an object, causing this object to move the distance or displacement of D, and the angle between the two is theta, so we have a cosine of theta here. But if you want to consider a force for displacement 1 with an angle theta 1, and then displacement 2 with an angle theta 2, and then 3, an angle theta 3, and then so on. And if you want to find the total work, you have to add these terms. So total work is the force on displacement D1 on an angle theta 1, and then for 2 the same thing, for 3 the same thing, and so on and so forth. So basically it is the area under the force versus displacement curve. In other words, if you have a force displacement curve or force D figure, then what you have from x1 all the way to x2, so this is the displacement or D, then whatever area that you have underneath, so this area underneath the FD figure will be the work done by the force, okay? So this is what it is. Now, if you're looking at this, we have a work done by a variable force. Here, first type, if the force is constant, as you can see, the force is a solid, horizontal line, just like that. And from x1 to x2, which is, this is the displacement that's happening. So this is our displacement from x1 to x2. So d is x2 minus x1. And force is constant. So if I find this area, which is one side times the other side, so F times D, it is exactly W, all right? If a force is constant, but we have this constant force is only applying for a specific position, for example, x0, x1, x2, x3, x4, I have from x0 to x1 a force of F0. From x1 to x2, I have F1, then F2, F3, and so on. So if I add these areas, okay, for example, S1 is the area inside this cube, and then I have a rectangle, S2, S3, and S4. So if I want to find the total work, I have to add them up. I have area 1 plus area 2 plus area 3, and so on and so forth, okay? Constant value of force, but it's change for different displacement. So we can approximate a continuous varying force. So here I have a varying force. It's F0, then F1, then F2, then F3, and so on, but it is constant through its elapsed time or elapsed displacement. So from x0 to x1, the force is constant, all right? But it is changing block by block, all right? Or in other words, on several successive constant values, okay? But here, it is in a constantaneous or continuous varying, and it's varying at each moment, okay? So I can approximate an area underneath this curve to be the add of all of these blocks. So I can say that the work, total work, is S1, S2, S3, and S4, okay? But this approximation is not a very good approximation. And that's the reason is obvious, because you are missing this area. These areas are missing, okay? So it's not a very good approximation. So what you need to do is to have these blocks to the maximum number they can be. So rather than just having 4 rectangles here, I can have more than 4, okay? 4, 5, 6, 7, 8. So I can say that the work, total work, is if I add everything. And it's a better approximation if you do that. So what you can see here is actually is a integral. So in other words, I can say that work is the integral of f times dx, f dx, okay, from x1 to x2. The integral of f, which is a variable force, from x1 to x2, okay? So this is the actual formula that a physicist or a physics student should use to find the work done by a force. So integral of x1 to x2 of f dot dx, all right? Let's take a look at a variable force that is variable and it depends on the displacement, just like a work done by a spring. So a force needed to stretch a spring of an amount of x is F equals kx. And remember, this is, if you go back to where we were talking about, I think it was in chapter 5, that we talked about the force of a spring. We said that the force of a spring is negative kx because the force and the displacement are in the opposite directions. In other words, if this is the displacement, okay, the force would be in the opposite direction. So that's why you have a negative there to indicate that they are in the opposite direction. Now, if you want to do that, what you need to do is here we're talking about the amount of the magnitude of the force. So what I have in order to find the work done is from x1 to x2, or usually the x1 is 0. So from 0 to x, I have f dot dx. Okay, so from 0 to x, all right, f is kx dot dx. This k is constant, so I'll bring it out of an integral. So I have w being k is constant for spring. I'll bring out. So I have 0 to x, x dot dx. Okay, so I have k, and we know what the integral is. Oops. This integral is half x squared from 0 to x. So k half x squared minus 0 squared. All right, so this is capital X that I have right there. So x squared minus 0 squared, or half k x squared, as you can see right there. So the work done by spring is half kx squared. You can memorize it, you don't have to drive it, but this is literally what it is, half kx squared. Okay, now the force required to stretch a spring is f of x is kx. Now this is depending on the distance of the spring to the stretch. So as I said, f of x is kx dot dx, and then k is constant, will bring out, and then I have x times dx, so, and it will be just kx squared, as I just drive it over there. Now the little bit of a confusion is that that you need to be very careful is whether to have this negative sign being included or not. So if you compress a spring, so we're talking about this negative sign, this negative. Should I include this negative when I'm to play? Okay. So let's see, let me share this one more time. There we go. So this is where this is coming to play. If you compress a spring, the force the spring exert on you, because you feel it in your hand, is opposite to the direction of the displacement. So therefore you have a negative there. So depends, you have either this or that. But if they ask for the magnitude, who cares about the negative or positive anymore at that point, correct? So let's take a look at this problem. We have a 0.4 kilogram block slides to the right on a frictionless surface with a initial speed of 2.5 meters per second until it reaches a spring. So we have the mass of the block being 0.4 kilograms. Okay. With a initial speed of 2.5 meters per second. And remember, this is frictionless surface, so this speed is not going to reduce because it does not have any type of friction until it reaches a spring. Okay, so I have a box going to the right on a surface, and at this point it is reaching a spring that is being connected to a wall. Okay, now when it reaches the spring, it compresses in a distance x before coming to momentarily stop. So in other words, the displacement here is x. Okay, if the spring constant or the force constant is k, and it has a value, it's been given to us, k is 450 newtons. Okay, how far is the spring compressed? Or in other words, find x for us. All right, so work energy theorem. Work energy theorem is saying that the total work is this. Is the change in the kinetic energy. So total work done is K final minus K initial. K final is 0 because it will eventually stop, even though it's momentarily, it will have a 0 velocity. So this is 0, we know that, right? Now, so I have negative Ki here, all right? Now, how many forces do I have? I have a mg down, right? So let me change the color. I have mg, I have normal force, and then I have, since this block is pushing the spring to the right, I have a force stored in the spring, and it is towards this direction, so F, which is towards the left. So I know work done by normal force is 0. I know work done by mg is 0 because they are perpendicular to the direction of motion. The cosine of 90 is always 0, okay? Because of cosine of 90 is 0. So the only force left is this force of spring, right? So if that's the case, then I have work done by spring force equals negative Ki right there, right? So work done by the spring force is negative half Kx squared equals negative half mv2 squared. Okay, why did I keep the negative here, or why did I have force of the spring being negative Kx? Because to indicate that this work is done by the spring and not by me, okay, and this is in the negative direction of the displacement. The displacement is to the right and the force is to the left, okay? So this negative and this negative will cancel out, they'll go away, all right? So I have negative half, we have a value for K, which is 450 newtons. So 450 x squared equals half of m. I don't know what the m is, which is given here, but 0.4 kilograms, I know it now, 0.4. V initial squared. V initial is 2.5 meters per second, so I have 2.5 meters per second. You know what, let's forget about the unit at this point. 2.5 meters per second square. And I have a negative here as well. Now, I can cancel out this negative with this negative, and then I am left with everything is known except this x squared. So I have x squared being half 0.4, 2.5 squared over, and something else that we can do here to give it a try, it's actually very good to do it, because not only this negative will cancel out, but also this this factor of 1/2 will also cancel out as well, okay? So then you have 450 here in the denominator. You have a 450 value. So 450, all right? Now, what it means is you can find x, or the displacement, just by putting the square root on top of everything. So you have 0.4, you have 2.5 squared over 450. So as you can see right there, I have found the displacement. The key of doing this was to understand that it has come to final velocity of 0. So I can find the delta K, or the change in kinetic energy. And I know the work done by the spring force. So I can relate them. And that's what I did. The reason I put negative here and include that negative, because it's the work done by the spring. And we know it's always in the negative direction of the displacement. So I keep that negative there with this, equations. So last example for this part of the video, example number 7, runaway semi-trailer. So a semi-trailer is coasting downhill along the mountain highway when its brakes fail. The driver pulls onto a runway truck ramp that is inclined at an angle of 12 degrees above the horizontal. So I have a ramp of 12 degrees above the horizontal, kind of like this. So this is a 12-degree ramp, all right? The semi-trailer coast to a stop after traveling 155 meters along the ramp. So in other words, I have moved 155 meters as my displacement up, okay, from this point all the way to that point. And eventually I will stop. So that means at this final point, the final velocity is 0 because I have stopped at that point. Okay. Now, if that's the case, using the concept of work and its relation to the kinetic energy, determine the truck's initial speed. And then it says, you may find it helpful to draw a diagram, which we always do in physics. Neglect air resistance and friction. This is also something that we always do. So I have a box. Let me actually draw it, or a truck, or a box, or whatever. I always use a box or something like circle or whatever that you wanted to write. So I have a box here, or you can have a circle, or you can actually draw a truck. It doesn't matter. And so what we're looking for is to find, we have the final velocity, we have an initial velocity of non-zero, and we know that it's 12 degrees above, and the displacement is 155, okay? We are looking to find the initial velocity, so that's what we're looking for, of initial velocity. Let's see what it is. So we know the work done is delta K, we know that, okay? The total work done. How many forces do I have here? I have mg down here, and I have normal force up there. What else do I have? I have no friction, and then that's it. So if you remember from previous chapters, if a force is not along the direction of motion, and it's not along, or it's not perpendicular to the direction of motion, it has to be break down to its components. In other words, I have to break this mg down to two forces. One is mg cosine theta, and one is mg sine theta. Okay, that's what it is. And so this mg doesn't exist anymore because it's been broken apart to its components. One mg cosine along the y direction or negative y direction, and one mg sine theta along the negative x direction. So in other words, when I'm looking at this, this is my coordinate system. I have a x and a y for my coordinate here, all right? So that's what it looks like. So I have x and I have y direction like that. Now, mg, the work done, okay, so the work done by normal force is 0, okay? The work done, because of the angle of 90 degrees with respect to the displacement, the work done by mg cosine theta is also 0 because of cosine of 90, which is 0. They are perpendicular to the direction of motion. The only force left is work done by mg sine theta, okay, which is F dot D. They are forces. This is the general formula, F D cosine theta, okay, between work and displacement. So let's actually write down 12 here to not confuse you. So let me actually go ahead and delete this, okay, and this, and write down here the actual value, which is 12. Okay, so 12. this theta is between force and displacement. Okay, so that's what it is. So here what I have then is F, the force, which is mg sine of 12. The displacement is d. The angle, the cosine of the angle between the force and the displacement, which is 180 degrees. So I have 180 here. In other words, I have mg sine 12, d cosine of 180 is -1. So I have m so here, let me write it this way. So in other words, what I have is work done by mg sine 12. This is work done by mg sine 12, okay? Now, where do I use this? I am using this right here. I am using this guy right here. That's the place that I want to use everything. So in other words, if I am looking at this, sigma W is delta K. Sigma W is work done by normal force plus work done by mg cosine 12 plus work done by mg sine 12. So this guy is 0. This guy is 0. I am left with mg sine 12, work done by mg sine 12, which is right there. And it is equal to delta K. So, so work done by mg sine, work done by mg sine 12 is K final minus K initial. And K final is also 0 because it will stop at the top of a ramp. Either way, this is 0. So I have work done by mg sine equal to -½ m v0 squared. So let's substitute everything now at this point. So work done by mg sine, I have it right there. It is -mg sine 12 times d. And over here on the right-hand side, I have -½ m v0 squared. When you're looking at this negative and this negative will cancel out. This m and this m will cancel out, okay? You multiply both sides by 2, so you have 2g sine 12 times d equals this 2 and this 1 over 2 will cancel out, so I have v0 squared. And v0 squared, or just v0, then would be 2g d sine 12, okay? And 2 times 9.81 times the displacement of 155 times sine of 12 under the square root. That would be your initial velocity. Put it in the calculator to see what it is. Okay, end of part 2 of the video. We're going to continue with part 2 right after this. In the third part of the video, we're going to talk about power. So next video will be part 3 of chapter 7.